Okay, so welcome to section 10.5, which is conics in polar form. Thank goodness, something finally where they're all easy now. Conics in polar form. So let's consider the following. So let's say we have polar coordinates, like so. Namely, this is 0, this is pi over 2, pi, 3 pi over 2. And let's say we have a focus at the pole. So that means that our vertex, for if we do a parabola, let me make that f a bit better, will not be at the pole. So let's say the vertex is somewhere down here. So here's our vertex. And let's have our parabola open upwards. So that would be something like so. Kind of. How do we get the kitty serenade? Okay. There we are. Kind of. Oh boy. Oh my goodness. My kingdom to be able to write or draw a bit better. Okay. Of course, my kingdom is just dead. Okay, so let's say we have a point P anywhere on this parabola. So I've got the distance from the focus to P, and what that does is it creates an angle theta. Agreed? Because remember, we're now in r comma theta, no longer x comma y. So I claim that, actually let me go ahead and draw my directrix while I'm at it. So here we have, I'm sorry, it's just the cat in the cat box is classic. I'm trying to focus. I'm trying to focus, Kitty. Okay, trying to focus on doing math. Yes, okay. Okay. At least I amuse myself, clearly. Have no friends. Okay. Where am I? What am I doing? I don't even know what I'm doing anymore. Okay. So, what should I do here? I'm going to call the distance here. I claim that this distance is sine, or rather r, if this is my radius. Oops. So say we've got a radius from F to P. I claim that the y coordinate is going to be r times sine of theta. All right. And then let's call the distance to the directrix from the polar axis. Let's call this distance little d. Okay. So now this is a parabola, which means that from the point P to the focus F, I'm sorry, she's really just, oh my goodness, a good time in there. Okay. If I weren't running out of time to get this done before the semester starts, I probably would re-record, but at this point, I don't know. I really don't know. Okay. Holy frilly. Okay, so we have that P to the focus is going to be the same as P to the directrix, because that's what the definition of a parabola is. So this would imply that there's going to be, well, how do I want to say this? For a parabola, do you agree that if I divided both sides by p times d, or not p times d, the distance from p to d, I would have to get 1, right? Because I would be reducing on the right-hand side. So I would get the point to the focus divided by point to the directrix would be equal to 1 on a parabola. Okay. Yep. Yeah. On a parabola. So hopefully that makes sense. Because they're equal, just divide both sides and we get 1. And let me reduce that a bit better. Okay, so given that, we know that P to F we called R. So P to F I called R. Right, it's a radius from the pole to P, which makes sense. But what about P to D? Let's consider P to D. And then we'll equate the two. I claim P to D is going to be R sine theta plus D, right? Little d. Okay? So the quotient, so this implies that P over F, P to F, distance from P to F, divided by the distance from P to D can now be rewritten as R divided by, in this case it's going to be, let me swap the order, D plus R sine theta. And we know that that, in the case of a parabola, is equal to 1 because it's equidistant, right? It's equal to 1 on a parabola. So hopefully you followed me this far. So now what I'm going to do, let's take this equation over here. And I'm just going to multiply both sides of this equation. Cross multiply, basically. So let's cross multiply the denominator. Because my goal is to isolate R. Because we always want to solve for R if we're dealing with polar equations. So D plus R sine theta gives me that R is equal to D plus R sine theta. So now I'll subtract R sine theta from both sides. So I'll get R minus R sine theta is equal to D. Factoring out the R, I get that R times the quantity 1 minus sine theta is equal to D. And now I can finally solve for R. Namely, R is going to be D divided by 1 minus sine theta. Okay, and that is true for a parabola. So I'm not going to do this for each of the conics because that is pretty close for us to let me show you how nice conic sections are. So theorem. The equation for a conic section, any conic section now, it doesn't, We don't need to differentiate between parabola, ellipse, hyperbola, anything. So the equation for a conic section with focus, with a focus, because it could be something else, with a focus at the pole, which is the origin, and eccentricity, well, let me put it this way, comma, eccentricity, little e, and distance to the directrix little d is given by number 1, r is equal to e times d divided by 1 plus or minus e cosine theta. And this is going to be a left-right conic. And number 2, we have r is equal to e times d divided by 1 plus or minus e sine theta. And this, of course, will be a down or up conic. But what is e? I didn't have an e up here. I had the d. What is e? E is this mysterious eccentricity. So let's get back to it. Where e less than 1 implies an ellipse, the eccentricity. E equal to 1 implies a parabola. Okay, so let's pause for a moment and go back to what we had up here. Do you agree that there is technically a 1 here and a 1 here? And that is the eccentricity. So it's actually there. It's just not explicit because we didn't know what we were looking for at first. And last but not least is the third type of conic. So if the eccentricity E is larger than 1, then this is an hyperbola. Now, this is going to be so much nicer when it comes to plotting these things. It's amazing. So let's go ahead and plot some because they're so lovely. Do I have enough room to plot on? Let's see, 1, 2, 3, 4. Oh boy, I don't know. Do I have enough room up here? Maybe if I rearrange some things. Let's put this over here and say this implies there. Can raise these up a bit. And now I should have enough room to at least do 1 on here. Wow, that didn't really seem to raise it up very much, did it? Okay, so for example, so plot the following conics. The following conics in polar. In polar. Plot the following polar conics. Maybe that sounds better. Plot the following polar conics. Sorry. It's a good thing there's not smell-o-vision. Okay, so here we go. Radius is equal to, let's do 2 divided by 1 minus 1/2 times cosine of theta. Okay, so this is already set to go. We have radius r is equal to 2. Well, what is 2? I claim that 2 is going to be 1/2 times 4, which is true, it is. But why did I do that? Well, this is 1 minus 1/2 times cosine of theta. Okay, so 1/2 is less than 1, so I claim that this is an ellipse. And I claim that D is 4, the distance to the directrix. And it's cosine, so let's see what happens here. So let's do our polar coordinates. So 0, pi over 2, pi, 3 pi over 2, okay, so usually in order to do polar coordinates, we would need to draw a whole bunch of concentric circles. So I guess we could do that as our grid. So something like so, etc. It would go on outwards. And then we would have the angles as well. But hopefully we won't need all of that. So there's always a focus at the pole. But what about the directrix? What about any other points? Well, the way I do this is I just plug in the coordinates. So at 0, I know cosine of 0 is 1. So 2 divided by 1/2 is 4. So I know 1, 2, 3, 4. The radius will be, actually, let me make that in purple. The radius will be 4 at 0 radians. At pi over 2 radians, cosine is 0, so I just get a radius of 2. At pi radians, cosine is -1, so I'll have 2 divided by 3/2, that's 4/3. 4/3 is 1 1/3. So that's my radius in the direction of pi. Then once again, at 3 pi over 2, cosine is 0, so I just get a radius of 2. So notice, this is my ellipse, not drawn very well. See, yeah, it's just going to give me a circle. Let me try and draw a better ellipse. And then, okay, so we've got an ellipse. Like so. There we go. There's our ellipse. Okay, but what about this mysterious directrix? Well, the directrix is at a distance of 4 from the pole in the direction 1, 2, 3, 4. Now, we're used to having negative cosine, meaning we open to the left. But now this negative here means the directrix is to the left. So negative implies directrix D is on the left. So now we're going to, that'll tell us the placement of the directrix. Okay, let's do another one. Wasn't that lovely? That was so much nicer. Okay, so number 2, let's say we have that R is equal to 3 divided by 1 plus sine theta. Okay, so we have radius is 3. But before I do 3, let's look at the denominator here. We have 1 plus what's attached to sine is 1 times sine theta. But in the numerator, we have 3 times 1. And let me do the 3 actually in green because it tells us how far the directrix is. So my eccentricity is 1. This means this is a parabola. The distance d to the directrix is 3. Positive sign means the directrix d is up. Okay, not the parabola. So if I didn't know that, let's see what we would do. So let's do a polar curve. So that is, we'll have 0, pi over 2, pi, and 3 pi over 2. We will have concentric circles. To create our polar grid. Okay, so if I have 0 radians, I know that sine of 0 is 0, so my radius is 3. And remember, there's a focus at the pole. If I plug in pi over 2, sine of pi over 2 is 1, so that gives me 3 halves, so 1 1/2 is my radius in the direction, pi over 2. If I plug in pi, sine of pi is 0, so my radius will be 1, 2, 3 in the direction of pi. Now, what happens when I plug in 3 pi over 2? Sine of 3 pi over 2 is -1. That's infinite. I can't plug it in. But do I have enough to plot my parabola? I do. And notice that this one automatically gives us the latus rectum. The latus rectum is always going to be one of the 2 axes, right? Come on. Okay, close enough for government work. Nope, not close enough. Okay, but where's the directrix? Whoa, holy fairly. Okay. Well, the directrix is 3 up, 1, 2, 3 from the focus. So here is our directrix, the positive sign or positive y-axis, right? Okay, so let's do another one. Notice they all have the same form. All conics have the same form in polar coordinates. They're so much easier. So let's do r. Pardon me. No, shoot. R is equal to 1 plus 3 cosine theta. So now we're positive cosine, which means that's where my directrix will be. So let's rewrite this. R is equal to, let's look at the denominator first. 1 plus 3 times cosine of theta. So in the numerator, I have 3 times 2 to get to 6. So my eccentricity is 3, which is greater than 1, so this is a hyperbola. The distance d to the directrix is 2. And I know because it's positive and cosine, this means that the directrix is going to be right, to the right. Okay, so let's see if that's true. So let's do, well, we've got 6, so we're going to have to go up 6 and down 6. Let's see if I can do 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, I can do it. That's good. Hopefully that gives us enough space. So x, oh, not x and y. What am I saying? 0, pi over 2, pi, and 3 pi over 2. And now we will put our concentric circles, or try to put our concentric circles to indicate the grid and polar, etc. Okay, you get the idea. I'm not going to do the whole thing. This doesn't need to be this long. Good enough. Okay, so let me move this so I have a bit more room. Okay, so I'm going to start at 0 radians. I know that cosine of 0 is 1. So 6 over 4 reduces to 3 over 2, which is 1.5. Remember, my focus is at the center. Okay, so now let's go to pi over 2. Cosine of pi over 2 is 0, so 1, 2, 3, 4, 5, 6. My radius is 6. Now let's go to pi. Cosine of pi is -1. So that'll be 6 over -2. So that's a -3. So in the direction of pi, I now have to go negative, which means I go 1, 2, 3 to the right. Okay. And now at 3 pi over 2, cosine is 0, so I go 6. So what's happening here? Let's see. Looks like I'm going to have part of my hyperbola, like so, which means that this other part is going to be similar. So I can take that 1.5. So 1.5. I should have a point here along the same line, 1.5. So it should be a mirror image on either side. Oops, does not look good. On either side. So that one point out, that one man out, is what we get to represent the other side of the hyperbola. But what about the directrix? Where does that come into play? I claim that the directrix is 2 units to the right of the focus. And that makes sense because we're going to open away from the directrix. And you might say, well, how come the line is closer to one side than the other? And that's because there's actually 2 directrices. We're only plotting one. So the only conic that has 1 directrix is a parabola. All other conics have 2. Okay, so now let's do, what should we do, one more for this measure? So, number 4. Number 4, let's plot r is equal to 2 divided by 1 minus 1/3 sine theta. Okay, so we get that r is equal to, let's focus on the denominator first, 1 minus 1/3 times sine of theta. So I claim the numerator, 2, is going to be 1/3 times, what, 6? Is that true? Okay. So 1/3. The eccentricity, eccentricity is 1/3, which is strictly less than 1, which means that this is an ellipse. I claim that the distance to the directrix is 6. And I claim that this is minus sine. This means that the location of the directrix is going to be left. Okay, so let's see. So let's go ahead and plot our polar axes. Sorry, not left. Did I say left? Wow, I must be tired. Down. Holy frioli. Down. Not left. This is sine, so it's up, down. Okay, where was I? We have 0, pi over 2, pi, and 3 pi over 2. Let's go ahead and plot our concentric circles. Okay. Okay, so I know there's a focus at the origin. Now if I were to plug in 0, sine of 0, 0, so my radius would be 2 in the direction of 0. If I were to plug in pi over 2, sine of pi over 2 is 1, which gives me 2/3 in the denominator, or 3 overall. 1, 2, 3 when I invert and multiply. Now if I go to pi, once again, sine is 0, so my radius is 2. If I go to 3 pi over 2, my radius is -1. Sorry, sine is -1. So I get 4/3 in the denominator times 2. So that's going to be, let's see, 4/3 is going to be 3/2. So I claim that my radius is 1.5. Okay, so let's go ahead and draw an ellipse here. Well, that's terrible. Let's see, I'll draw an ellipse like so. No, I cannot. Wow. There we go. So now I can take this ellipse and make it fit here, hopefully. Or at least I can try. Okay, good enough. Okay, but what about the directrix? The directrix, I claim, is down 6. 1, 2, 3, 4, 5, 6 from the pole. Okay, there we are. So that's how much nicer all conic sections are in polar coordinates. They're very, very nice. So easy. Okay, that's it for chapter 10. I will see you in chapter 11.